Right. Work now? Okay.
And did you unmute it?
Yeah. We'll see. All right.
Please sit down and let me join the speaker, Ulrich. And I will be talking about quite interesting topic, FPGAs. It will not be about Python mining, but about the architecture and stuff.
All right, so I heard already some people frightfully asking me, will it be as hard as yesterday? Yesterday was the easy part. Today, you better be an EE to actually understand things now. So I actually kept it very simple. So it's just the basics there. So, but still, let me ask, anyone actually has done any work on FPGAs? Well, yeah, a couple of people. So, of course, this is a topic which came up much more prominently in the last couple of years because as I explained yesterday, CPUs are woefully inadequate to actually do the computing we are forcing them to do. And if we actually can provide some piece of hardware which can do this in a much better way, why not? And in theory, in the olden days, this meant, well, you had to go and actually create an ASIC of some sort, try it out and see whether it works, and then reiterate until you actually got to something which was far, far too expensive. So fortunately, we had for quite a long time something which mainly existed in the embedded realm, which are these FPGAs, field programmable gate arrays. And the field in that part just means that it can be reprogrammed on the fly. That's the part which we're going to talk about. So where is it coming from? So in general, we want to provide some form of device which can do universal compute of something. So we have an idea, we code it up in some way or form as a function. We have variable inputs, and we get the appropriate outputs in it. So in the past, as I said, we could do this with pure hardware of something there. For those, hopefully you appreciate that I use the 555 there. And on the other hand, we can write a computer with a general CPU which can execute any kind of code and implement the function there as well. So neither of them is perfect. So computers are very good, of course, when you have very high variability, etc., and very high complexity. But on the other hand, well, they're sequential for most parts. Even though we have parallelism, of course, the parallelism level is very low. So on the hardware side, it's actually not that flexible to program. Once you have it, you're done. So the good thing is with FPGAs, they're fitting somewhere in the middle. That's what we're going to talk about here. So, but before I go there, I have to go through a couple of things on both on the software side implementation, on the hardware side implementation, to actually, for you to appreciate why we have such a nice thing as FPGA, which have advantages in certain areas. And on the software side, I'll make it very simple. Yesterday, I talked about the Skylake core, well, just briefly and so on. This time, I go to the other extreme. This is the 8085 core. I couldn't go possibly any simpler. That's the most simple microprocessor out there, the first one out there, actually, first reasonably out there. And that's a complete diagram. So just let's take a look at how actually instructions gets executed on this thing and how the individual parts which make up a CPU are actually used. So on the left-hand side now, you see this is something which I took more or less from the Intel manual, which describes the 8085 or 8080. And it describes the different states in which a single instruction gets executed. So even simple instructions like move instructions actually were executed in many different individual steps. Nowadays, this would be completely hidden. The internal stepping and so on is completely hidden from the user and so on. Instructions are marked as being executed in a single cycle, etc. But in those days, they were completely exposed. So we had memory steps, so the memory clock cycles, the M cycles, and each M cycle had a couple of sub-cycles and so on in which they were executed. And the table on the left-hand side specifies us for 3 different types of instructions. I'm not going through all of them. I'm just looking at the LDA instruction, which is load the accumulator, special register. And the whole thing starts by exposing the current address to the address bus of the CPU. So because at this point, it's not even clear that we're executing the LDA instruction. This is simply what the CPU does anyway. And now on the right-hand side, you see in the diagram of the CPU, which are the parts of the CPU which are actually active at that point. So at any point in time, the timing, etc., on the decoding parts, which is implemented as a PLL on an X80, on X8080, are active, but the other parts are the active parts actually, which make up a CPU, which are the variables which actually implement the different types of action the CPU can do. So in this case, for exposing the PC, the program counter just to the address bus, it's very simple. Only the register containing the PC is necessary, and then the address buffer and the address by itself. So this is done here in the first subcycle of M1. The second one, at that point, we have to wait for the memory to react. And the CPU uses this as for housekeeping. In this case, we have to make sure that the next time we access the memory alongside the instruction stream, we get to the next byte. So there's a special piece of hardware in the processor, which is an incrementer, not an adder. It's just an incrementer, which adds 1 to the PC. So just this tiny little piece of the CPU is necessary. So those pieces together probably just make up a fraction, 40 transistors out of the entire 4,000 transistors of the 8080. So a tiny fraction of the whole thing actually is active at this point. And this continues to be the case. So in the next step, we have loading from the data bus, get the bytes in. So at this point, we actually know, oh yeah, this is an LDA instruction. The decoding happens in the next cycle, which is, again, the CPU can do nothing. It's just does the crunching of what does it mean actually that I loaded now the byte which represents the LDA instruction. So in the next cycle then we can finally start the work. In this case it means, well, the LDA instruction requires 2 bytes as an argument. So the next 2 bytes in the instruction stream are the address from which we actually have to load. So we first have to expose the PC again to the address bus. We have to wait. And while we are waiting, we are incrementing the PC. We are loading the byte, and we are storing it in a temporary register. Then we have to load the third byte. Again, increment the PC while we are waiting for memory, loading from memory, and storing it in another register. So now the WZ as a double register contains the address, so that finally now we can execute the load of the appropriate memory location and then redirect this into the appropriate register. So the property of these last 2 cycles there is that they are actually overlapping with the M1 cycle of the next instruction. So, which means that whatever I showed at the M1 cycle there before, which is loading from the PC, the next byte of the instruction stream, happens in parallel to this. So this is actually one of the more busy cycles. But what you have seen is that pretty much nothing which the CPU does keeps the entire CPU, the entire core implementation, as you can see it here, busy. Only ever a tiny little piece is active. And that has been a property of CPUs ever since. We have tried the CPU manufacturers have tried to implement various ways to increase parallelism, to issue multiple instructions at the same time. But if you look at the entire transistor budget, which is available to write nowadays a modern CPU core, it's still a tiny little fraction. So it's a huge waste. And if we wouldn't have all this power gating, which happens nowadays in the CPUs, we actually would also have quite a lot of energy waste. So, and even with that, it's not as efficient. So if we really know what we are going to do, all this dynamism which we see by the CPU reading an instruction stream and so on, and which comes along with the uncertainty, what is the next action which we're having to do and what we have to prepare for. If we know ahead of time what the action is that we want to actually implement, we can do much better. Because if we have all the transistors available, which a CPU core has, we can put them to use all at the same time in parallel. So the situation is really not that different today. So, as I said, a couple of things changed. We have wider data buses. So internally, we have now a multiple of 64 bits, which we can transfer in parallel instead of just 8 bits. We have wider internal buses. We have more registers, not even registers. We have what's called now register files, which make it much more possible to actually execute things in parallel. We have wider registers. We have more capable ALUs, so the arithmetic and logic units, which can actually perform arithmetic and logical operations and so on. And we have multiple of them to issue, to work on multiple instructions at the same time, etc. So, but this all means that on the modern CPUs, we just have more things which are sitting idle. That's the picture from yesterday from the Skylake core, how it looks like. And look at all this stuff in there. So just these pipelines which you see for the arithmetic ports, which are attached to port 0 and port 1. These, I don't actually want to know how many millions, hundreds of millions of transistors are behind these things, because they are incredibly complicated. A multiplier, a 64 by 64 multiplier. I don't actually know what the exact number is. I think at some point I heard a 32-bit by 32-bit multiplier is in the order of 100,000 transistors or something like that. The 64 by 64 is much, much more than that. In addition, you add what all these, you have vector registers now. So it's not 64-bit, you have 256-bit or 512-bit. And that for every single core. And all this stuff lays there without being used if we have a dynamic instruction stream. So the same is true also for the memory accesses. So yesterday I was harping a lot about the inefficiency of the memory subsystem of the CPUs which we have nowadays. And the problem is, again, the dynamism in the system. So if we don't know what the next instructions are going to do, well, we have a problem. On the other hand, maybe you have actually heard about for all these, for instance, cameras which are out there, which can take 100,000 pictures in a single second. And maybe you have asked yourself, there's a processor in there somewhere. How do they read this out and can write this memory, this to memory, this stuff? Well, guess what? They don't use a normal CPU for these kind of things. And they have access patterns to memory which are known ahead of time. And for that, we don't have the same problems as we have for normal memory accesses. We don't have to work with these workarounds like cache lines and even pages and all these kind of stuff which we have invented for the CPU for operating system purposes, but also just for the caching and efficiency purposes. We don't have to deal with these kind of things if we know how the application actually performs, what it wants to do, what kind of memory access it wants to do. And if we are thinking of in the HPC context about these things, and we have operations like matrix or tensor multiplications, and there we know exactly what the memory access pattern is going to be for a long period of time. So instead of having the CPU second guess ourselves every single time and mispredicting and clearing caches and all these kind of things, if we can actually write something which takes advantage of this knowledge ahead of time and doesn't, and therefore we can also, for instance, attach the memory which we know will only be accessed by a certain part of the CPU only to that CPU, not the other one. So we are eliminating bottlenecks inside the processing unit. We can achieve much better performance. So another thing with a normal CPUs is, at least for server side specifically, but also even down in this case to the embedded side, is connectivity to the outside world. One of the purposes of these small embedded processors is that they can actually attach using protocols like GPIO or I2C, etc., all these bus protocols to devices on the outside and actually, well, control them or read them or whatever way you want to actually use this kind of thing. So for the SoCs which are out there, this is to some extent possible because they have everything on the chip itself. So they have RAM, they have the processor, etc., all on the one chip. So the outside connection for them to function are minimal. They just need the power supply, perhaps a clock gating, etc., reset pins and so on. So that on a normal package, So you have enough free pins to have these connections outside. Well, the same is not true for a normal CPU. So if you look at the normal CPU itself, so we are already spending a huge amount of time, aside from all the hundreds of pins which are necessary to run the power inside the chip. We have to spend quite a lot of pins for the connection to the memory subsystem. So nowadays, for instance, some big Intel core has something like 4 memory controllers, or some of them have 6, or at least some of the AMD ones have 6 memory controllers with all the hundreds of lines which are going out to them. So they're eating up a lot of the budget there. There's simply a limit, a physical limit of how many pins you can have. So just look at the motherboards which you have now on a PC or on a server board. They are 7 or 8 layers. That's insane if you want to try to route these kind of things. So there's a certain limit which you can do. And the nice thing, again, about what we're going to talk about here, the FPGA side, is that we can eliminate many of these things as well. We can have we have freely programmable pins in there, as we can see, which we can use for any purpose. We are not tied to what someone who is at the fab thought about the individual pin is for. So we get the best with FPGAs of that we can do whatever computation we want to do at a very high speed if we actually implement it right and we buy the right chip. And we can also do everything which is done on the embedded front with one single type of chip. So now let me, yes?
For the pins to be functional, like on the fly, you need a routable board, right?
Yes. Well, the question was for the pins and so on to be usable. The board, of course, has to support these kind of things. So if you want, you can later on come. So I have actually a couple of FPGAs with me. You can look at them. So they are very flexible normally in this sense. Even the simplest boards, you can route them out. But the point there is simply that these are just usually. If you buy a development board, they're just there for you to take. So they're routed out. There's a pin there, and you can attach something. And with modern designs and so on, with one of the boards, you can see this. It's a very, very small board. So it's just like 4 by 5 centimeters or something like this, which has 200 and something pins available for you to program. Do this with a normal, even embedded processor. It's not really that easily doable. All right, so I've talked now about the software side of the original slide which I had there. So now let's talk a little bit on the hardware side there. So I'm not going into why this is so different and so on. Here at that point, I have to concentrate on what is the thing about the hardware side which we have to take on to actually utilize FPGAs. And that's a part which I can easily spend an entire week talking to you about, because this is quite honestly a class in IEE which you have to visit to actually understand everything about this. So I will concentrate on just a couple of highlights and so on. So everyone hopefully knows that at the basic there, so we have at the basic level, we have transistors and so on, and transistors, even in its most rudimentary form, we can implement something called gates, which is the basic unit in which we are designing electronic circuits. So, and in logic by itself, the most prominent ones, so in mathematical logic, are operations like AND and OR, which have these two truth tables. Everyone hopefully knows about that. What everyone hopefully also knows is these are not universal gates. Universal gates are those which allow you with just that gate to implement any other operation by itself. So on the other hand, universal gates are the NAND and the NOR. It's surprisingly just inverting the output of an AND or an OR gate makes them into universal gates. But it's clear, so if you want, you can actually run the mathematical proof that you can implement any kind of logic with a NAND gate or a NOR gate or a combination of them, etc., etc. So that's one of the two of the most fundamental gates. And here at the top, you see how I can implement an AND gate and an OR gate, so just replacing them. It's very simple in its nature. And the nice thing about this with the MOS logic, so NMOS, PMOS, CMOS, and so on, the NAND and the NOR implementation are actually much easier than the AND and the OR implementation. So it all fits together really, really nicely. But there's one more gate, which some people, especially if you're not into EE and into CMOS design, are ignoring, and that is the multiplexer. The multiplexer is also a universal gate. It has, in this case, 3 inputs, A, B, and then S as in selector, and that's the output appropriately. And it's just very simple. So if the S decides which of the 2 inputs is routed to the output, that's it. That's a universal gate. And this one thing is the key to actually understanding how FPGAs are working. So how does it work so basically? At the core of every FPGA is something called a LUT, a lookup table. Here's the simplified version, a 3-bit, which you will hardly find at all anywhere in any kind of hardware implementation nowadays. Nowadays, they have more than 3 inputs. But for the sake of you being able to read things, I restricted myself in the representation here to a 3-bit one. So you see there a cascade of these multiplexers. So, and hopefully you realized how they actually can be used. At the bottom, we have 3 input lines, A, B, C. And on the left-hand side, you have these boxes, which are 0 and 1. So if A, B, C, in this case, are our variables, our variable inputs, and A, B, C are pre-programmed patterns, so either of them you put in 0 or 1, and you fix it. With that, you can implement any function of 3 inputs. So it's similar to what I said before about the multiplexer before, but in this case we have static information, which are these left-hand side boxes here, which are usually implemented in FPGAs as really very fast SRAM cells. So these are pre-programmed and they stay fixed for the duration of the run until they get reprogrammed. And all the inputs are just these signals, the selector signals. And with that, we can get whatever output we want. So let's play with that. So for instance, if I want to implement a 2-input AND function, so we have 3 inputs there, A, B, C, but I have a 2-input AND. Well, which means one of them, we should have an ignore signal. So we should not take advantage of the information of anything in there. So with that, it means that, for instance, the C signal in this table here is ignored, and A and B are the inputs. So it's very easy to decide how I actually have to program the SRAM cells. You just put up the logic table on the left-hand side. I've ordered them in exactly the order in which the A and B signal are selecting the multiplexer outputs. So from the bottom up, so 0, 1, 0, 1, 1, 0, etc., all these kind of things. And then the Z, the output column of my lookup table there, of my truth table, actually not lookup table, of the truth table, corresponds to this is how I have to program the SRAM cells. It's very simple. So we can repeat this for the OR operation in a very similar fashion. And we can also have it for a little bit more complicated one. In this case, a full adder, a 1-bit adder. It's one of the most fundamental operations I will have later on for you if you don't know that. So don't worry, I have this in more detail in one of the next slides. So a full adder we can easily implement with that as well. So this is just the sum of the full adder, not the carry. But nevertheless, I can implement this with a 3-input LUTS. So in general, again, it can be proven that this is a general, universally programmable function. I can produce for any output, any result. So how can we use this kind of thing? So in an FPGA, well, up till a couple of years ago, 2 or 3 years ago, FPGA programming was really the realm of the specialists, and you had to use the proprietary tools. So I know until 2 years ago, I exclusively had to use, I never used Altera, I always used Xilinx. and I had the Xilinx tools, the ISE IDE. You download it, it comes as 40 gigabytes or something like this of code, completely proprietary code. It never really works well, and it's clumsy like hell, but yeah. The big IDE companies also, like Mentor Graphics and so on, they're selling you even more sophisticated tools on that, and this is what you had to use to actually program FPGAs. So a couple of years ago, there's a guy, specifically the guy here on the bottom right, it's Clifford Wolf, actually not far from here, he's living in Vienna. He actually, with the help of a couple of other folks, reverse engineered how a specific FPGA based on a chip by a lattice called the ICE40 works from the ground up. So we know now how to program this thing. And these are the two chips which I have here are basically based on that family as well. So this is why we can use this so quickly. So we actually have now a freely available tool chain for this thing from source code. I have the source code for that on my laptop. I can compile the tool chain. I can use it to compile completely sufficient and completely running code on these FPGAs. These are small FPGAs. These are meant for really small embedded applications, but it's a start. And if you should have at some point any interest in or looking for a project to do, I highly recommend that, and if you have any interest in EE, try to see whether we can re-engineer and reverse engineer some more of the protocols. Because the vendors, the FPGA vendors, they're telling us, oh, we are not telling you about the protocol, and we are encrypting all the data for your own protection. Yeah, bullshit. So we have to do something about that because, as I said, this is one of the ways how we can actually increase the efficiency of programming dramatically. And we can see now a little bit more once we are talking about how the specifically, in this case, the ICE40 is working. And then we'll go to a little bit of code, and you can see how this all fits together. So on the ICE40, as I said before, I introduced the LUT. The IC40 has a 4-bit LUT, so not the 3 has a 4-bit input and so on. Just like any FPGA, it's based on that, and it's not standing alone. All the FPGAs have some logic cell, some minimal cell, which is the constituents of everything else in the chip itself, so almost everything, and so on. So for the IC40, it's very simple. You just have the LUT. You have a D flip-flop for the output, for the buffering if necessary, and you have some additional logic in this case. So this box here at the top left side, which is the carry logic. I'm going to talk about this in a bit. So these are the only things there. So the things which are programmed statically, so when you're initializing the chip, an FPGA chip, you're sending in some configuration which is static for the duration until it gets reprogrammed, are the things which are associated. Let me see whether I can actually have a, oops, nope. It actually crashed. Blame Fedora. So Denise's fault. Yeah. Where are we? Okay, here. All right. So I was talking about the top left there. Basically, this is the logic. So the things which are statically compiled are programmed is this little selector. Here's a multiplexer, which is statically programmed, which selects between the line coming here and the I3 line. The LUT itself, of course, in this case, how many bits are in the LUT programming? It's a 4-bit LUT. The 3-bit LUT had 8. The 4-bit LUT has 16. It's not that hard. Just follow. Then we have the top selector, the multiplexer. There is another bit. So in total, this thing is programmed by 20 bits. So these bits by themselves are used in groups. Lattice calls them logic blocks, PLBs, programmable logic blocks. And in this case, they are grouped by 8. Very convenient if you want to do 8-bit computing, because now comes this carry chain into play. So again, on the next slide, I talk a little bit about adders and so on. But in basically what this means is, with a group like this, I can actually implement very, very easily an 8-bit adder. And with multiple of these groups, because the signal actually can continue to be passed to another group of 8, I can very easily produce a 32-bit or whatever adder. But now comes one of the big kickers. I can also write very easily a 7-bit adder without wasting resources. So one thing which we have in computers all the time, so in normal CPUs, is they're only really efficient in handling data which are multiple of or power of 2. Once we are going down to the logic level, we can program at any size and not waste the resources. All right, so in this case here, so this is the next level up, as I said, in the ICE. And we can implement the adders and so on. So we have, in this case, at LUTS, we have 33 inputs and a couple of controls. It's very nice. So I talked about the adder, so I thought I had to inject this because I don't want to assume that everyone knows how this works, because this is really one of the fundamental logic cases which you need to understand. So on the left-hand side, you see what is called the half adder. It just takes 2 input bits, in this case A and B, and produces the sum, and it produces the carry. The carry is just the overflow. So 2 of these together, as you can see it on the right-hand side, are making a full adder. In this case, you have the 2 inputs. You also have a carry in, and you have a carry out, and you have the sum. Ignore the Q and the P part. So I simply took the graph from some other presentation which I have, which gets a little bit more complicated, so I don't want to do this here. But this is basically exactly what you can implement with one of these. Come on, one of these here. So the carry part can be implemented using the chain on the left-hand side. The top one is simply programmed as outputting a 1 if at least 2 of its inputs are 1. And the LUT can be programmed whatever you want. So you can therefore implement with this thing, with a chain of these, an adder of arbitrary size. And again, arbitrary size means not even just power of 2. So yesterday we had a brief discussion about designing floating point circuits for exactly the precision which you need. Guess what? With FPGAs, it's very simple. You know ahead of time how much precision you need, instead of having to live with floats of 32 bits, so a 23-bit mantissa or a 53-bit mantissa. I can say, I can live with 36 bits. And the difference in time it takes and in energy spent between 53 and 36 is significant. We can do that. So multiple adders, so continuing the same thing, can simply be chained like that, and we can do this by themselves. So I don't say this is efficient. I just say this is very easy to implement. On your normal CPU, adder is not implemented like that. That would be too slow. This is called the ripple carry adder. Hopefully someone has heard about that actually at some point. Ripple carry adders are what you learn in kindergarten, basically. So this is not how you do things nowadays, really, if you need performance. So adders are supposed to finish their work in a single cycle, and ripple carry adders, as soon as you have a certain size, are simply too slow, because the information, the overflow can actually initiate from the lowest bit and has to propagate all the way down at every single gate in the middle introduce a delay. So that's not possible. Nowadays, you have much more parallel versions of that. So, but at least for these low-end versions of the FPGA, which we have in the form of the lattice, we have a possibility to very efficiently implement adders, because if we wouldn't have this carry chain, we would have to implement the carry chain explicitly with a second LUT, which is slower. So in this case, it's very efficient. So in the same sense, we also have other FPGAs, so more complicated FPGAs, which are not having only support, native support for adders in there, but they have support for multipliers in there. It used to be until a couple of years ago, they were a scarce resource. So you had FPGAs, even the big ones, with a couple of hundred multipliers in there. Nowadays, because it's so prevalent to have these kind of things, you get massive numbers of multipliers potentially if you pay for it in your FPGA. So this is just something which the manufacturer can make a decision about when it is. And you can make a decision when you buy the whole thing. How much multiplication do you need? How quickly does it have to be? If it doesn't have to be quickly, well, then you implement a multiplier with adders. If you don't, if it has to be quick, well, then you get hardware multipliers. And the nice thing is that from the programming perspective, this is actually not that problematic. So I'm going to talk about how we program these things very quickly. So, but the main thing here is that for the cell here and so on to be useful, they're put in an even larger context. So everything which you saw on the previous slide are these POBs. In the smallest version of the ICE, it looks something like this. This is the 1K version. So this has approximately 1,000 lookup tables. And it's already somewhat usable for certain things. It has also, every FPGA usually has some RAM blocks in it. So this is dedicated static RAM, which can be accessed and so on, and which extends the amount of data which can actually be stored at any point in time, just like in a computer. So it's not just we have to have active state in the form of state in the flip-flops at the end of each of the cells, but also in the form of RAM. We have this available. So, but now you should ask yourself, well, what does it bring us? We have now hundreds of little processors in this thing. How do they actually work together? And this is where the real genius of the FPGA comes in. Because if we now would have to specify, oh yeah, I want to have the output of this specific LUT being available through a connection at this side, well, that would be so by itself is a task. If you want to have a free specification of that, it's actually pretty hard to do. On the other hand, if it forces you to have the output of this LUT is only available here, well, that's too restrictive. So what FPGAs have are what I highlighted here as yellow. There's an interconnecting network there, which is the result of many, many decades of research, how we actually do this kind of thing in a way which is efficient, but also doesn't require that much state to actually program. Remember, we need about 20 bits for each of the logic units there, and a little bit, so multiply this by 8, plus the sampling control bits for each of the PLVs, and then we have, 60 or 32 PLVs and so on. So it multiplies, but we also have to configure the connections. And the whole thing is that each vendor, each producer of FPGAs came up with his or her own set of connection rules between the individual blocks. And as I said, there has been lots of research in this area to make it somewhat usable, especially for the pattern which we expect. And every single chip differs there. So part of the reverse engineering of a chip is find out how the connection network works. That was one of the main things. So I took the pictures here more or less. So I redrew them. So I took the pictures from the iStorm documentation, which is what Clifford Wolf and the guys did to reverse as a result of the ICE reverse engineering. So they came up with these drawings. So we have a horizontal network, which is the one on the left side. So this is how there is a horizontal connection between the different PCBs, and you see there's a certain kind of shifting going on. It's not just a plain navigation there. And on the right-hand side, this is the vertical connection network. And for each of those kind of things here, so there is somewhere a programming bit which can be set. So basically, you say this connection or this input is used, this input is not used, and so on. That's a limited set of those. This is a good, it's a good compromise between having completely static rules of the connection and having completely freely programmable. So just network switches, think network switches connection, which is simply impractical. This is the middle ground. And the connection bits for the whole chip, for the ICE chip, is something like, I think I have this later on, is here. So this is for a normal chip. It's for the logic cell, it's 20 bits. For all of them together, this is for the smallest version on something like this. For each of the logic blocks, we have 8 of them in there, so 160 plus all the bits which describe what connections are going to work. So these are always on this chip specifically, 5 bits which are necessary, etc. So the details you can read up in the documentation and so on, but it's very interesting that this describes completely how an individual logic block is configured. Multiply this by a number of the logic blocks which exist on the system, and it looks something like this. In addition, you have the configuration of the I/O, which is the pins on the outside, which connect the system to the outside or to the RAM and all these kind of things. So as that, even on the smallest FPGAs, you can have dozens on even modest, these really, really still small sizes and so on. You can have hundreds of these output pins, and they can be freely routed. You have access to them, and you can do whatever you want. On the very fast ones and so on, there, for instance, if anyone is trying to come up with a new Ethernet standard, so for instance, when they started working on 100 gigabit Ethernet, well, they didn't have to go initially to ASICs right away. They programmed this using FPGAs. It's easily doable. So, and run config is the last one. So how do we actually get this in? So we are talking about what's called the bitstream. That's the terminology which is used in industry for that. So all the configuration bits which you saw on the last slide are collectively called the bitstream. We have a tool chain which can produce this. So we are normally starting with source code in the form of either Verilog or VHDL. These are the 2 hardware description languages which are most dominantly used. The tool chain which we can freely use here for the ICE and so on is a Verilog tool chain. So I personally, it's very much C-like. And VHDL is a language which is coming from US government, and has specified this, and by its heritage, it's Ada-like. It's, in my opinion, a little bit easier to use because the tool chain catches more errors by itself, so to some extent. So. But in any case, you have a tool chain, a compiler, which does kind of think, and I can show you this on the last slide, and so on. It produces the bit stream, and this is a binary file, which can be either stored in the flash on the FPGA itself. So usually every FPGA has a little bit of flash somewhere where it can directly read its bit stream from, or you can program it from the outside. Usually there's a USB interface. There's an FTDI chip which has the translation from serial to USB attached. These things are tremendously cheap, and every board has some, and you can easily connect your UPC to it with a USB cable, and voila, you have it programmed. Then it runs. But the main thing is that it doesn't run just the code by itself. It runs it in the FPGA way. And that is, it runs in parallel. But before we can actually do that, we have to understand something about the difference by normal code. And this is something which is alien to software developers. And that is the difference between synchronous circuits and asynchronous circuits. So just take a look at the little gate which you see up there. It's an AND gate or something like this. And I have inputs A and B, and I've shown you here. This is timing diagrams. They're usually shown in something like that. So, and I have indicated there as with delta t something which delays the signal a bit. So if the signal is not delayed at all, the output z will always be 0 in the ideal case. But as soon as you have a little bit of a delay, you get a strange output mix. And delays are usually accidental. They're normally not something which you want to have, but you have to deal with them. And now imagine you have a very complicated networks of LUTs and so on connected from one place to the other. And you really don't know how long the signal propagation takes for you to actually get to a stable result once one of the inputs changes. If you would write your entire circuit as a synchronous signal where you always depend on the output of any kind of a gate directly and immediately, you might see these intermittent, strange results, and they can be problematic. So it's possible to design circuits this way, but in general, circuits are designed with in a synchronous fashion. And this is where the D flip-flop, which you saw in the LUTs, in the logic cells, comes from. The D flip-flop simply has here's the simplified version, has the property that as long as the clock signal it's usually edge triggered in this case. So this is what this triangle shows. So as long as there is no signal on the clock, it simply outputs the previous state. And as soon as the clock signal is handled, it takes on the D inputs, and from that point on uses that one. So this one is able to actually deliver a stable output based on the clock signal. This is why computers have clocks. Very same reason. So with that, if we just create a phi signal, so a clock signal which clocks at the appropriate time, even with delta t, which is greater than 0, we can achieve the right results. This is how we are designing the circuits, and this is why the logic cells have this D flip-flop in it. And it's part of the tool chain's work to actually make this work. But synchronous doesn't mean sequential. The whole point we have behind FPGAs, and why I was explaining at the beginning why we have the CPUs which are doing all these things sequentially, we want to write things in parallel. And here's a tiny little bit of in this case, Verilog code to show you how a program looks like. So this I actually can show you running on one of my tiny little FPGAs. This is just doing some blinking of the onboard LEDs. So the point here is that besides specifying some registers and so on, so how the main parts are these always blocks, which you see there. This is not sequentially executed. They simply, you can imagine them as being loops which are running all the time, completely in parallel. And in general, there are hundreds, thousands of these kind of things in a complex design, which are running and producing kinds of results. In this case, for instance, it runs all the time, but it says that, oh yeah, I'm doing the following work only if the clock edge is changing. In this case, it's a rising edge. So, and then we have things like this, which look like variable assignments, but they are not really. These are just merging of signal lines with certain operations, in this case, an XOR operation. So languages like VHDL and Verilog are combining, are actually pretty good at combining, expressing this parallelism which is going on with a high-level programming semantics, which allows you to use combinations or operations like, in this case, XOR, and it is up to the tool chain to actually implement this for you. So to use this code, which you have seen on the previous slide, we would use on the IceStorm toolchain. That's the name simply of the ICE toolchain, which we have available there for free, with this couple of commands here. So we have the first command is IOSIS. This is the program which translates the, in this case, Verilog, into in the format, the BLIF format, which describes the operation in terms of whatever the device, in this case, the ICE40, can support. So if we have multipliers available, it would, for instance, also have a line there, yeah, maybe use this multiplier, or use a multiplier of some sort. In this case, we don't have multipliers, but there's a board description basically available, says what is available, and this has to be very target specific, but the toolchain should ideally be generic. So then comes the Arachne PNR. PNR stands for place and route. That's the part which takes this general description of what the program has to do and instantiates this for the specific FPGA. So puts it on this grid which you see of all these logic blocks, which you saw there. It determines what is the best connection there, and so to minimize the delays and the amounts of cells which are used, etc., and these kind of things. So this is you can imagine this is a big sets over. So this is decades of research went into how to write this in a very nice way. So ice time is just, in this case, optional. It's timing analysis. So if you have specific dependencies and so on timing, you would run this. IcePack creates the final binary bitstream out of the whole thing, and iceproc downloads it, in this case via USB, and you can play with it. So again, I have this, if you want, available on my system and so on. It's really trivial to do. So someone actually took the task and actually wrote a visualization of how it actually looks, how the program, the bitstream, once it's loaded, looks like. So I apologize that it's not really that readable. This actually is someone who wrote JavaScript code. This is code runs in your browser and visualizes the whole thing. It's no easy way to do this kind of thing. So, but in general, here is a blow-up of the code which you just saw, where we have, remember, we had the two counter registers. And here, these sequences here, where you can see here, this is just implementing the 23 or 24-bit adder. And you see them being nicely chained. So you could analyze everything, and in the browser you can hover with the mouse over, you see all the connections, etc. and so on. It's really, really nice. Anyway, so I have to stop now. So, but in general, we have problems when it comes to the kind of operation we do. We have hardware dependencies and so on, which makes it very hard to just say, I buy this FPGA and program this. So this is why I have to rely on the vendor tool chains, and we have to actually work actively as a free software community to make this available, to actually get the tool chain more capable to handle more and more of the chips, but also in general, just unlike in a normal operating system environment, we cannot start with the idea of something like an operating system behind everything. Unless we buy what is called IP blocks, we have to start from scratch. We have to write the code for an Ethernet controller. We have to write a TCP stack or a memory controller. Even something like accessing DRAMs and so on is usually not available. So we have to write these kind of things as well as blocks and make them freely available for everyone to use. All right. So the last thing, and I know I'm over time. Come on. Is that there's a nice mixing between the software programming and the pure hardware side of the FPGAs. And that's actually what I'm mostly interested in. This is why I'm using FPGAs, is that we can implement what is called soft cores. So we can implement CPUs, normal CPUs, ARM CPUs, or whatever, and emulate normal instructions which you can execute a normal ARM CPU, for instance, on this thing then. So I don't use ARM. I'm actually working with a platform called RISC-V. And even on my tiny little one, I actually have a Pico RISC-V implementation on there. And I can experiment with the whole thing. I can design new instructions and whatever. And especially with an instruction set like RISC-V, which allows us to set aside certain ranges of the instruction encoding for our own purposes. You can imagine that I can write my own instruction, which says, decode the picture which is at this address and perform an FFT on it. I can make this a single instruction. This is the way how computing has to work in future. And we don't have to compromise by requiring everyone to do everything from scratch in VHDL and Verilog, as long as we can write our own soft cores, which then can execute with sufficient speed the specialized instructions which can come up with. All right, that's it. I put it back in. Hey, Larry. Well, there are multiple things. Yesterday I talked about, I had this in my slides here as well. Intel has